Okay, now we're getting into more complicated diagram rating. First, let's start with some simple question. And if the stress we apply to this material is 400 Pascal, and what is the strain under this stress? And we mentioned that earlier. It's pretty easy, and just need to find where's the corresponding strain under 400 Pascal. In this case, gonna be about strain equals 0.39-ish, right? It's not too hard. And if you look at that point, if we let's call this point X. Let's look at this point X. We know the point X already passed the yield strength, right? It's in the nonlinear region. This is the linear region of the diagram. And we know once it passes the yield strength, and permanent deformation occurs in the material. And the corresponding strain here include all the elastic deformation as well as the plastic deformation. Okay, so this is not too hard. And what if I ask you, what if we release or we remove this 400 Pascal stress? What happens if you release the stress? And when you release the stress, and the material would go back partially to its original shape. It would not recover 100%. Let's draw a diagram to show that. So this is the original length, the material we test. That's the original length, L0. And after we apply this sigma equals 400 Pascal, our new length is L1. And we know the strain here is 0.39. And what happens after we release this stress? We know this bar will go back to try to go back to its original shape, but it can't, right? Instead, it probably can go back to this much. And now we have this small part right here, let's shadowed area. And this is the prominent deformation caused by this 400 Pascal stress. And it couldn't recover to its original length L0. Let's call this L2. The total new length is L2. And let's call this small region. And the plastic strain we try to find. And how can we find out what is the strain after you remove the load? And this is the find elastic recovery after plastic deformation. This belongs to this problem. Okay, we can use a 5 steps approach to find the elastic recovery after plastic deformation. Okay, now let me show you all the steps. Let's call this 5 steps approach. Okay, step 1, is to determine the type of deformation. Determine the type of deformation under the given stress. In this case, our stress equals 400 Pascal. This is plastic deformation or permanent deformation. And if this is the case, then we need to jump to step 2. And if this stress is smaller than the yielding stress, that means you only have elastic deformation, then we're done here. We can just get a conclusion right away. And the conclusion of the plastic strain is going to be 0. Or you can say delta L after you release or remove the stress is going to be 0. Because it's inside of elastic region, the material acts like a spring. Once the load is removed, and it can go back to its 100% original length. Right. Step 2, if in this case our stress is larger than the yielding stress, we have plastic deformation. And step 2 is to find the point corresponding to the applied stress on the curve. Let's call that point X. In this case, this is our point X. Okay, step 3 is to draw a line that passes that point X. Not only pass through X, but that line need to be parallel to the linear segment of that stress strain curve. Okay, let's do that. Okay, now I use the red line to draw a parallel line, and then at the same time the line should pass the point X. Okay, so this red line here is parallel to this linear line in the linear region. That makes sense. And also this red line is passing through the X point X. This is step 3. Step 4 is to find the intersection point. Let's call that point Y. And this is the point that is corresponding to the plastic deformation strain after you remove the stress. Okay, we know here is our intersection, and the readout here is about 0.09. Okay, let's put it here, and this here is 0.09, and that is the strain when you remove the load and still left remains in the material, if that makes sense. And in this case, we know after this load is released, and this bar will try to go back to original shape, but still have this sigma equals 0.09 deformation left in the material. And if we want to find out what exactly is the change of length or the new length L2, we can apply the equation how we define sigma. Sigma equals delta L over the original length L0, right? So we know this is 0.09. We know the original length. Let's give original length to this problem. Let's assume it is 1 meter. And we can find out what is the change of length delta L. In this case, would be 0.09 times 1 meter. We have 0.09 meter as the change of length. If we want to find out what is the new length L2, simply use original length plus the change of length, and we end up with 1.09 meter. So that's the new length after this load is removed. Right down here, 1.09 meter. Okay, now you can see this bar start with its original length 1 meter, and once you apply this load to this bar, and it elongates, right? It becomes longer, and L1 we can definitely do a quick calculation about L1. L1 gonna be 1.39 meter in this case. If the load is released, then the length become 1.09 meter. All right, so hopefully this 5-step approach will teach you how to find out